Welcome to the Sky Commander Flight Brief. It's your mission-ready podcast for drone pilot training and aerial insights across Canada.
From Transport Canada rules to real-world drone ops, we break it down, take you higher, and help you earn your wings. Because here at skycommander.ca, we don't just fly.
It hints there's more to it. It's a masterclass, a deeper level, maybe a philosophy or a community focus, perhaps.
It's definitely intriguing, sets them apart from just, a basic tips show. Skycommander.ca is the obvious next step. Precisely. If you're thinking about flying a drone in Canada, boom, this content is aimed right at you.
Powered by skycommander.ca.
The elite podcast for Canada's drone pilot. Okay, let's get started. Today, we are moving past what you might call the 101 level of drone operations. We're going to strap in and really get into the language of certified, scalable air services.
That's right.
If you've been following the conversation around commercial UAS, you know the basics. You've heard C2, you've heard DAA.
Sure, the Tier 1 stuff.
Exactly. But if you want to fly beyond visual line of sight BVLOS and actually talk the talk with regulators, with engineers, with serious investors, you really need that next layer.
You do.
So today we are deep diving into the dense, sometimes frustrating, but absolutely essential vocabulary that designs, quantifies, and ultimately justifies the entire BVLOS safety system.
And that's a critical distinction, isn't it? We're moving beyond that Tier 1 vocabulary, which, you need just to understand the technology.
Right.
We're getting into Tier 2, which is all about risk and geometry, and even Tier 3, which is that global regulatory crosswalk.
So this is about fluency.
This is 100% about achieving fluency. You shouldn't just know what an operational design domain is. You need to understand how the ODD defines the robustness your hardware has to have.
Okay.
Our goal here is to get you to the point where you can articulate risk like an operations designer, someone who can build a repeatable, auditable safety case.
And the context for this is really important right now. We're anchoring this deep dive in concepts from the proposed U.S. rules. Specifically, that big notice of proposed rulemaking, docket FAA 2025-1908, that came out in August 2025, and the related Part 146 proposal for service providers.
And it's key to remember, even though they're proposed rules,
right,
these concepts, ODD, DAA assurance levels, ADSB certification, they aren't just being invented by the FAA. They're all derived from shared international standards, from groups like JERIS and ISCO.
So this isn't just theoretical jargon.
Not at all.
Yeah.
This is the skeleton. It's the skeleton that the entire professional infrastructure is being built on, and not just in the U.S., but globally.
So whether the final rule is called Part 108 or something else,
it doesn't matter. The safety logic is immutable. Every single BVLOS operation, at its core, is a quantifiable risk problem. And this vocabulary, this gives you the tools to solve and, just as importantly, justify that equation.
Okay, let's get into it then. Let's start with that fundamental shift, the whole philosophy of moving from, flying with your eyes to flying with technology.
The contrast is everything. VLOS, visual line of sight, that's the Part 107 world we all know.
That's home turf.
It is. The pilot or the observer, they are the primary safety mechanism. They're using their unaided sight to see the aircraft, to know where it's going, and, critically, to avoid other aircraft. That basic see and avoid rule.
So safety is immediate, it's sensory, it's very human-centric.
Exactly. But the second you fly BVLOS beyond visual line of sight, that entire human-centric safety net just, it collapses.
Yeah, if I'm inspecting 50 miles of pipeline, my eyeballs are completely useless.
Precisely. BVLOS means your operation is now managed entirely through procedures and technology. The shift is from relying on human sensory data and sort of instinct to relying on systemic, probabilistic safety assurance. It's a huge change. We use technology like detect and avoid systems, strategic deconfliction, robust C2 links to maintain a safety level that's equivalent to, or hopefully better than, that human eyeball.
So Part 108 is really just about making that technologically managed risk routine.
Routine and scalable. It is the codification of all the risk mitigation you need when you take the human out of that direct control loop.
That trade-off is fascinating. You gain all this efficiency and scale, but you're replacing intuitive sight with, auditable documentation?
You have to. It's mandatory. When you submit your justification to the FAA, you're providing engineering proof that your system's performance is predictable and reliable within these very defined parameters for the whole flight. That rigor is what unlocks the economic value of BVLOS.
And to make that proof work, you can't just fly anywhere. You have to define the boundaries of that safety case, which brings us, I think, to the ODD.
The operational design domain.
And this is so much more than just a flight area, isn't it?
Oh, it is the single most important definition in all of BVLOS operations. The ODD is the comprehensive set of conditions. It's everything.
Yeah.
Under which your entire UAS system has been designed and, crucially, validated to operate safely.
So like a contract.
It is the contractual limit of your approval. If your approval is for a BVLOS operation, the ODD defines the terms and conditions of that approval.
Okay, so what goes into a really robust ODD? We're talking geometry, but also the environment, services.
We use the memory aid BWOC XCS, which I find really helpful. Boundaries, objects, exposure, environment, and services.
BWOC XCS.
So boundaries and objects, that's your geographic limits, specific corridor coordinates, and known obstacles like towers or power lines.
Right.
X is for exposure. That's really traffic density. It's categorized by something called the Air Risk Class, or ARC, which we'll get into.
Okay.
Environment is what you'd expect. Weather constraints, max wind speed, temperature, visibility, even known RF interference zones.
And services, the S, that's the external stuff you're relying on.
Exactly. The required supporting infrastructure.
Mm-hmm.
Are you relying on a certified UTM or an ADSP for deconfliction? Things like that.
And the origin story for ODD is interesting. It didn't even start in aviation.
That's right. It came straight from the automotive world, specifically the SAE standard for self-driving cars.
No kidding.
Yeah. They needed to tell people, look, our self-driving feature works, but only when the weather is clear and the lane markings are visible. It was a perfect fit. So UAS regulators, especially JARIS, imported that concept wholesale. It's an auditable framework for defining the limits of an automated system.
So the big implication is the ODD isn't a suggestion. It's the mathematical input to your entire risk equation.
Absolutely. If you step outside your approved ODD, say it's approved for 25 knot winds and you're flying in 30, your safety case completely collapses.
It's just gone.
The moment you're out of ODD, you are operating outside the parameters under which the FAA deemed your system safe. For a professional operator, violating the ODD isn't just a regulatory failure. It's a fundamental breakdown of your engineered safety assurance.
Okay, so that's the sandbox we're playing in. Let's talk about the lifeline, the C2 link. Why does Part 108 treat this radio link as a safety-critical airworthiness topic, not just, a connectivity issue?
Because the C2 link is the nervous system. It's carrying commands to the aircraft and bringing critical telemetry back position, altitude, system health. In BVLOS, if that link fails or even just degrades severely, the system is immediately vulnerable.
The crew can't intervene.
They can't. They've lost their connection. So we have to move beyond just looking at subjective signal bars and start talking about verifiable engineering metrics.
What are those metrics? What does a C2 system have to guarantee?
Well, the requirements are pretty rigorous, and they're rooted in standards from groups like RTCA. Professionals are focused on 4 key performance areas. First is integrity. Can you trust the data? Is the packet corrupted? Second is continuity. How likely is the link to stay available for the whole flight? This is often expressed as a message success rate, or MSR.
And you need that to be really high, I assume.
For high assurance links, you might need an MSR of 99.9% or even higher.
Yeah.
Then you have availability, which is a percentage of time the link is actually usable. And finally, you have latency.
The delay.
The total time delay between the pilot issuing a command and the aircraft actually doing it.
And latency is a huge deal for BVLOS. Yeah. If you've got, say, half a second of latency, your ability to tactically avoid something with stick inputs it's pretty much gone.
It's severely compromised. And that's why C2 link performance is often tied directly to the SAIL level, the safety assurance level of the whole operation.
So a riskier flight needs a faster link.
A high-risk, high-SAIL operation might demand a round-trip latency below 150 milliseconds. A low-risk one might tolerate more. And this kind of rigor, it came from big historical programs like NASA's high-altitude research vehicles.
Right.
They had to prove they could rely on a satellite link enough to fly safely alongside airliners. Part 108 is just applying that same engineering discipline down to small UAS.
So the professional conversation isn't about signal strength anymore. It's about documented handoff procedures, calculating link margin, and proving your means of compliance. Your MOC shows you meet standards like RTCA DO 377.
Precisely. You have to demonstrate that your system's performance is predictable across the entire ODD. That means pre-flight analysis, avoiding known RF shadows, and having tested pre-planned loss link procedures that trigger automatically the moment integrity or continuity drops below a certain threshold.
So a loss of C2 isn't a surprise event. It's an expected failure of the system.
It has to be treated that way.
Okay, so the C2 link ensures control. But the biggest risk in BVLOS is obviously hitting someone else. We need a replacement for the pilot's eyes. This brings us to that 3-layer conflict management stack.
Right, and the first layer, the most immediate one, is DAA, detect and avoid.
Replacing the eyeball.
That's what it is. It's a technical substitute for the human eyeball, designed to meet that historical see and avoid rule when the pilot can't actually see. It's a combination of sensors, complex algorithms, and crew procedures to detect conflicts, predict them, and then execute maneuvers to remain well clear.
What makes a DAA system good enough for Part 108? It has to handle two very different kinds of traffic, doesn't it?
It does, and it does that through layered detection. First, you have cooperative detection.
The easy one.
Well, the ideal one. This relies on other aircraft broadcasting their position and altitude through transponders or ADS-B. If the traffic is cooperative, detection is relatively straightforward and accurate.
But the hard part is the non-cooperative traffic.
That's the hard part, detecting traffic that is not broadcasting. Small planes, gliders, military traffic, or just an aircraft with a broken transponder. This requires much more complex sensors.
Like radar.
Onboard radar, acoustic sensors, or really sophisticated electro-optical cameras paired with AI object recognition. The complexity is it's astronomical, especially when you think about the closure speeds between a slow drone and, say, a helicopter.
Right, and the goal is to remain well clear.
Exactly. The DAA algorithms have to constantly calculate the time to closest point of approach, the CPA, and execute an avoidance maneuver with enough margin to guarantee safety, especially when the other guy's intentions are a total mystery.
So that memory hook, DAA equals detect, anticipate, avoid.
You need all three.
You need all three. If your system only detects, but it takes too long to calculate the avoidance or the maneuver is too weak, you've failed the requirement. And this has huge implications for hardware certification. A DAA system for a high-risk flight might require really high design assurance levels, or DALs.
Okay, so DAA handles the immediate tactical stuff, but we need a strategic system to stop conflicts before they even have a chance to start. And that's UTM, Unmanned Aircraft System Traffic Management. UTM is that digital ecosystem designed to manage the density and complexity of low-altitude drone traffic.
And to be clear, this is not a replacement for a traditional air traffic control.
No, not in controlled airspace. It's a networked, automated system for flight planning and deconflation below where most manned aircraft fly. The analogy people use is the 1956 Grand Canyon collision,
which led to modern ATC.
Right. We need this digital infrastructure now to preemptively manage the chaos before it happens in the low-altitude sky.
And in the proposed U.S. framework, the critical component making this work are the ADSPs.
Automated Data Service Providers, certified under the proposed Part 146. And this regulatory split is vital to understand. Part 108 regulates the operator safety system, but the operator relies heavily on a certified Part 146 service provider, the ADSP, for critical services like deconfliction and monitoring. The ADSP is like your data sidekick, managing the shared digital sky.
I see. So there's a clear division of labor. The operator has operational control under Part 108, but they're buying safety services from the ADSP under Part 146.
It creates a trusted, regulated third party. And none of it fundamentally works without remote ID, Part 89.
The digital license plate.
That's exactly what it is. Yeah. It's the baseline infrastructure, broadcasting who you are and where you are so that everyone in the system, the ADSPs, ATC, law enforcement, can see you and hold you accountable. Remote ID is the data foundation that allows ADSPs to even function.
Okay, so let's walk through those 3 layers of conflict management again, because they're sequential safety barriers.
Right. This is the structure of safety assurance for BVLOS. Layer 1 is strategic deconfliction. This is the planning layer.
Happens before you fly.
Before you fly. Handled by the ADSP or the UTM system. You file your 4D flight plan, that's space and time, and the ADSP checks for overlaps with other scheduled UAS or known manned routes. If there are overlaps, it helps negotiate or automatically adjusts your plan.
So it's preventative medicine.
It is. Then, once the mission is live, you shift to Layer 2, conformance monitoring for situational awareness, CMSA.
CMSA.
This is a continuous automated check that your aircraft is sticking to its approved 4D trajectory and staying inside its ODD. If the drone drifts too high or too far sideways, the CMSA system flags a non-conformance.
So it's not looking for a collision. It's looking for a deviation from the plan. It's the glue.
It's the check on integrity. A CMSA alert means your flight is deviating from the assumptions of your safety case. And if you ignore it, that non-conformance could lead to a tactical conflict.
Which brings us to layer 3.
Tactical deconfliction. This is the DAA system's job. This is the real-time safety net. If strategic failed, maybe because of an unscheduled helicopter, and CMSA failed to get you back on track, tactical is your last line of defense. The DAA system detects the immediate threat, predicts the CPA, and commands a collision avoidance maneuver in real time.
So the model is strategic keeps you apart, CMSA keeps you compliant, and tactical saves you from the unexpected.
And you have to demonstrate to the regulator that you have all 3 robust, independent barriers in place.
Okay, now let's get into the really specialized Tier 2 vocabulary, the language of risk quantification. It starts with the benchmark, right? How do regulators even know if an operation is safe enough?
The benchmark is the ALR, the acceptable level of risk. And for complex operations, this is a consistent number. The US BVLOS RRC recommended a benchmark of 10 to the minus 7.
Which means?
It means the operation should result in no more than 1 fatality per 10 million flight hours. When an operator uses the term ALR, they're claiming their engineering mitigations meet that highly quantitative safety target.
That's a powerful number. So how do you build the case to prove you can meet it?
You use the SORA framework, Specific Operations Risk Assessment. It's the international standard. SORA breaks the risk down into manageable pieces to figure out how rigorous your mitigations need to be.
And it starts with the ground.
It starts with the GRC, or Ground Risk Class. This assesses the danger to people and property below you. It looks at the drone's kinetic energy and then applies mitigations based on where you're flying, a sparse field versus a crowded stadium.
Okay, so GRC is what's below us, then we look up.
That's the ARC, or Air Risk Class. This classifies the airspace based on the statistical likelihood of running into a manned aircraft. ARC categories go from A to D based on traffic density data.
And those two, GRC and ARC, combine to give you the most critical metric of all, SAIL.
SAIL, Specific Assurance and Integrity Level. This is the heart of SORA. It's a scale from 1 to 6, determined by a lookup table that maps your GRC and your ARC. And that SAIL level dictates the required rigor of your entire safety case.
Let's get specific. What does required rigor actually mean? What's the practical difference between a SAIL 2 and a SAIL V?
The impact is profound, especially in your avionics and software development. At SAIL 2, the requirements might just be procedural, documented maintenance, basic training. But if you're pushed to SAIL 4 or V, you are moving into highly rigorous design assurance requirements. For instance, a SAIL V operation might demand that your DAA software be developed to DO 178C standards at design assurance level C.
And a SAIL 6.
At SAIL 6, the highest level, you might need DLA software, which is the same level required for systems whose failure is deemed catastrophic on an airliner. It means extensive military-grade documentation and testing for every single line of code.
That's a massive economic hurdle. That's millions of dollars.
It's the cost of assurance. And finally, that SAIL level dictates your OSO, the operational safety objectives. This is your final checklist of mandatory requirements. If your SAIL is high, your OSOs are stringent, and you have to prove with your MOC that you've met every single one.
So once we've quantified the risk with SORA, we have to map that risk onto physical space. This is where those geometry words come in.
This is all about containment. We start with the flight geography. That's just the intended, planned 4D volume of your flight. It's the corridor you told the ADSP you're going to use.
But you need buffers around that.
Absolutely. The first buffer is the contingency volume. This is the defined space you've allocated to handle normal operational errors. A GPS glitch, a little drift from a lost link. It sits just outside the flight geography.
And what's the absolute maximum space the drone could possibly occupy?
That is the operational volume. It's the flight geography plus the contingency volume. If your system is working as designed, the drone should never breach the operational volume. This is the space you are telling the regulator you have total control over.
And the risk outside that volume.
That's the adjacent area, or adjacent airspace. This is the territory, a populated area, a highway, a restricted airspace that you have to protect if your containment fails.
I see.
If your drone enters the adjacent area, it means your engineering has failed. So the required integrity of your containment system, your geofencing, your geocaging, is directly linked to how bad it would be to breach the operational volume and enter that adjacent area.
So if the adjacent area is a school, your containment has to be basically bulletproof.
Precisely. You'll need exceptionally robust, probably redundant containment systems. The geometry defines the risk, and the risk defines the required technological rigor. It moves the conversation from where can I fly to what must my system guarantee.
Let's shift to the administrative and human side. The words you use when you're justifying, certifying, and auditing the whole organization.
Well, every BVLOS operation begins with a story. That's the CONOPS, the concept of operations.
The narrative blueprint.
It is. It's the document you give the regulator, explaining your mission, your aircraft, your ODD, your crew roles, and most importantly, your mitigation strategy, how you plan to handle the GRC and air key and achieve that required sail.
And once the regulator buys the story, you have to provide the proof. That's MOC and DOC.
MOC is the means of compliance. This is the technical documentation, the test reports, the engineering analyses that proves your C2 link, your DAA system, all of it meets the performance requirements. The MOC is the evidence.
And the DOC is just the legal statement.
The Declaration of Compliance. It's the formal legal statement by the manufacturer or operator affirming that the MOC is accurate and the system is compliant.
But compliance isn't a one-time thing. It's got to be continuous. That's the SMS.
The safety management system. It's not just a manual on a shelf. It's a living, continuous organizational process. The SMS identifies hazards, assesses risks, and continuously improves safety based on operational feedback.
So it's fed by the data from the flight.
It's fed directly by the data from your CMSA and DAA systems. Every non-conformance, every near miss, every lost link event, it all goes into the SMS pipeline for analysis. It drives proactive changes to your ODD or your procedures.
So an SMS is what makes an operation sustainably safe and auditable.
Precisely. It's the organizational commitment to safety that lets you scale. The FAA and Transport Canada both require a formal SMS for complex operations because the safety burden is shifting from the individual pilot to the organization's processes.
And that shift fundamentally changes the definition of a pilot. Under Part 107, it's all on the remote pilot in command. Under Part 108, it's on the organization.
The primary liability rests with the organization, which has to define and train specific roles that manage the system, not just fly the aircraft.
So what are these new roles?
The highest level role is the operations supervisor. This is the mission commander. They have overall operational control. They make sure the CONOPS is being followed, the ODD is respected. It's a strategic role focused on compliance and systemic risk.
And who is actually watching the screen?
That's the flight coordinator. They're tactical. They're actively monitoring the live missions, watching the telemetry, interpreting DAA alerts, responding to CSSA flags. In a scalable operation, you'll have one operations supervisor overseeing the whole fleet and several flight coordinators each managing a handful of aircraft at the same time.
So the training has to shift dramatically. It's less about stick skills.
And much more about system management, data interpretation, and executing pre-planned contingency procedures under a high cognitive load. You're training someone to manage probabilities, not just physics.
That makes sense.
And liability and responsibility are clearly segmented by these roles, which emphasizes that system-level understanding.
Okay, let's talk about Tier 3, the global perspective. Everyone is tackling BVLOS at the same time, so knowing the regulatory crosswalk seems essential.
It is. The core safety logic is standardized by bodies like ICO and JARIS, but the labels are different everywhere you go.
Let's do the US versus Canada translator.
Okay. The US uses UAS unmanned aircraft system. Canada uses RPAS remotely piloted aircraft system. It's a subtle philosophical difference. Canada historically emphasized the human pilot element more.
Right, remotely piloted.
While the FAA focuses more on the entire system, but in practice, the technology is converging. The US has UTM for UAS traffic management. Canadian guidance explicitly says their system, RTM RPAS traffic management, is a synonym for UTM.
So they're the same thing.
Functionally, yes. Same for DAA. The U.S. talks about the DAA system, the tech package. Transport Canada regulations often talk about detect and avoid functions. Again, functionally identical, just different legal phrasing.
And the regulatory tiers themselves.
The proposed U.S. Part 108 for routine BVLOS aligns almost perfectly with Canada's highest assurance category, Level 1 complex operations. These require a full RPAS operational risk assessment, which is basically Canada's version of the SRI process.
So if we look over at Europe, the vocabulary changes again, but the architecture is the same. They talk about use space.
U-space airspace, or UAS geographical zone, is the European term, and it maps conceptually to the digitally managed low-level airspace we're talking about in North America. U-space is legally defined airspace where certain services like network ID and conformance monitoring are mandatory for all UAS operators inside it.
So the U.S. is proposing to mandate services based on the complexity of the flight, while Europe defines the airspace itself as requiring those services.
That's the key difference in regulatory approach. But the underlying architecture is identical. Reliance on certified digital service providers to manage separation and conformance.
Mastering this really makes you regulatory bilingual.
It does. You can talk about a Part 108 corridor with UTM and DAA in the U.S., or a Canadian Level 1 complex up with RTM, or a European flight and use space. You're describing the same robust safety architecture 3 different ways. And that convergence is intentional, driven by global bodies like ICAO, pushing for a single set of performance requirements.
Okay, let's put it all together. Let's apply this vocabulary to a couple of detailed scenarios to see how it guides decision-making in real time.
Let's do it. First, a routine rural corridor inspection, say 30 kilometers of power line. It's approved for Sale 2, so low to medium robustness.
Okay, so the briefing starts. The operations supervisor is confirming the ODD limits. Rural Class G airspace, 150 to 350 feet, AGL, max wind 25 knots. And we confirm the MOC documentation proves the C2 link meets the required MSR of 99.8% across that whole corridor.
Right. And our ADSP has already handled strategic deconfliction. The pre-flight check confirmed our flight geography has 0 conflicts with known manned traffic, and we have our airspace authorization from the UTM system.
Okay, we're in flight. An unexpected thermal column pushes the aircraft up, and it climbs to 360 feet. What system catches that first?
The CMSA system, Conformance Monitoring for Situational Awareness. The aircraft is now outside its authorized 4D trajectory. It's breaching the vertical boundary of its flight geography. This triggers an immediate CMSA alert to the flight coordinator.
So it's a compliance failure, not a collision threat yet.
Exactly. The flight coordinator gets the alert. What's the protocol? First, they immediately check the DAA system status.
Okay.
DAA confirms the airspace is clear, so there's no immediate air risk. They issue a corrective command via the C2 link to descend back to 350 feet. And because the aircraft never even entered the contingency volume, which might go up to 450 feet.
They just log it as a minor nonconformance.
And that log is automatically fed into the organization's SMS. The SMS analysis later finds that crosswinds exceeded the 25-knot ODD maximum in that specific segment. So the operations supervisor might decide to refine the ODD for next time, maybe by reducing the max wind speed.
And that's the full loop. Planning, execution, monitoring, improvement.
The whole cycle.
Okay, now for a much higher risk scenario. An urban infrastructure inspection operating under a shielded operation concept. This is probably Sale 4 or higher.
Right. If we're targeting Sale 4, our systems has to be way more robust. We're talking DLC software assurance, maybe. Our ODD for a shield out would be incredibly strict, maybe defining lateral limits within 25 meters of the structure.
And the C2 link would need rigorous testing for multipath interference in that urban canyon.
You'd need documented MOC proving it works in that specific, highly reflective environment.
Okay, now imagine a major event. We're flying at 300 feet, and suddenly the ADSP pushes a high-priority constraint. Emergency services have declared a temporary flight restriction in our adjacent airspace.
And it overlaps our vertical profile. This is a strategic deconfliction failure. The unexpected happened. The CMSA system immediately flags a predicted nonconformance. Our current path is about to violate the new, dynamically updated ODD constraints.
So the flight coordinator sees the alert. What's the priority?
The priority is tactical deconfliction and maintaining containment. So the flight coordinator commands an immediate automated maneuver that was defined in the CONOPS for exactly this scenario. Maybe a high-rate descent to 50 feet to get out of the newly restricted volume.
This shows the layered safety concept working. Strategic failed, CMSA warned, and the coordinator executed a tactical response.
And the fact that this was a Sale 4 operation meant we had the redundant sensors and a highly assured containment system to execute that maneuver safely. The complexity of the maneuver, the rapid ODD change, the required integrity, it was all a direct consequence of that initial SOAR analysis that gave us that high SAIL level.
This whole deep dive really shows that using these precise terms, ODD, SAIL, CMSA, it's how professionals manage uncertainty. So what's the final takeaway?
The power is in the standardized, quantifiable structure. This vocabulary lets you take any unique, complex, uncertain BVLOS challenge and map it into a modular, risk-based framework. You can articulate the exact assumptions you're making in the ODD, the rigor of your proof in the MOC, and your systematic approach to safety in the SMS.
It provides clarity, justification, and it's auditable.
It's the difference between a vague description and a statement of validated system performance. Using this language, discussing C2 performance assumptions, strategic deconfliction protocols via a Part 146 ADSP. That is the single clearest indication that you understand how to design, justify, and execute a scalable professional BVLOS enterprise.
Well, that was an absolutely essential deep dive into the language of advanced BVLOS. If you can fluently weave together concepts like ODD, SAIL, CMSA, and the rules of Part 108, 146, you are not just ready for the future of drone regulations, you are ready to design it.
Before we wrap up, here's a provocative thought for you to explore. We talked about the acceptable level of risk, the ALR, being set around 10 to the -7 fatalities per flight hour.
Right.
As technology improves, as C2 links approach 5 nines of integrity and DAA systems become near perfect, the safety performance of UAS may statistically begin to exceed that of manned general aviation. So if the engineering reality changes the risk profile that much, how will regulators be forced to redefine or even lower the ALR in the next round of rulemaking? Will they create regulatory parity or maybe even an advantage for automated systems?
The idea that better technology might actually raise the required standard of safety across the board, that is a fascinating dynamic to consider. That's a wrap on today's mission, Commander. See above, go beyond, get ahead. For more training, tools, and intel, head to skycommander.ca. If you learned something new, share it, subscribe, and leave us a 5-star debrief.